Brajesh Muwel. This is my DS623 assignment on polynomial regression. In this video, I will show you Python's experiment I built to demonstrate what polynomial regression is, how the polynomial degree affects the result, and why using legendary polynomial is better than the standard approach. Now the problem Now the problem I'm solving is this. Imagine a weather station recording temperature every day for a full year. The sensor readings are noisy, meaning each reading has a small random error in it, but there is a real pattern underneath all that noise. Temperature rises in summer and falls in winter. It follows a smooth seasonal shape. The question is, given only those noisy measurements, can we build a mathematical model that recovers the true underlying pattern? Looking okay, now let's go into the code. The here the first cell only describe the three libraries, NumPy, Matplotlib, and NumPy's legendary module. Okay, so this second cell generates our data. The true temperature follows a sine curve, giving a smooth seasonal shape for across 365 days. I then added random noise to simulate real sensor readings. On the plot, the blue dots are the noisy temperature we observed. The dashed black line is the true pattern, which in a real situation we would not know. We only have the dots. The entire goal of polynomial regression is to recover something close to the dashed line using only the dots. Okay, so this slide shows the same scatter plot for reference. You can clearly see the seasonal shape. Temperature are low at the start of the year, rise towards the middle, and fall again at the end. The formula at the bottom is the model we are fitting, where t is a polynomial up to degree k. The coefficients are found by minimizing the total squared error between the model prediction and observed value. This is the least square method. So here is the fitting function. I pass in the data and degree k. The NumPy's polynomial polyfit solves the least square problem internally and returns the best fit coefficient as a callable polynomial. So now this is the most important result of the experiment. I fit three polynomials, degree 1, degree 6, and degree 20, and plot them side by side against the same data. Starting with the left panel, degree 1, this is just a straight line and the MAC is 31.9. It completely misses the seasonal curve because the straight line cannot represent a curved pattern. This is called underfitting. The model is too simple. The middle panel is degree 6. The MAC is 2.25. The rise and fall of the seasons is shown well here. The MAC is 2.3, which is much lower. This is a good fit. The right panel, degree 20, the MAC is 1.2, even lower than degree 6. But look at the shape of the curve. It is bending sharply up and down to pass through individual noise points that are not part of the real pattern at all. This is called overfitting. If I use this model to predict temperatures for a new year, it would perform very poorly because it learned the noise, not the actual trend. This shows why a lower training error does or not always mean a better model. So this slide shows the same comparison clearly. Red is degree 1, underfitting, green is degree 6, good fitting, orange is degree 20, overfitting. The MSC values confirm that lower error does not always mean the model is actually better. Now this cell now next we have training error versus degree. So this cell computes training error for every degree from 1 to 21 and plot the results. The error drops steeply at the start as the model learns the real structures in the data, but after around degree 6, the curve flattens out and barely changes. At that point, adding more terms to the polynomial is not improving the model. It is just memorizing the noise. The green dashed line here marks the degree 6 at the right choice. In practice, to find this automatically, we can split our data into training set and a test set and pick the degree that gives the best result on the test set. This process is called cross validation. Now the last part in this experiment is numerical stability. When we build the design matrix using powers of t, columns of 1, t, t squared, t cubed, and so on, a problem appears at higher degrees. This column begins to look very clearly similar to each other. High powers of t behave in similar ways over a limited range of data when matrix columns are nearly identical. The matrix becomes difficult to solve accurately. Small errors in the input data can produce large errors in the computed coefficients. We measured this using the condition number. A large condition number means the matrix is sensitive to small changes. A condition number close to 1 means it is stable. Looking at the plot, The trend line is the monomial basis. As degree increases, the condition number grows over rapidly. By degree 70, it is already in the billions. This means the tiny noises in the data could cause the computed coefficients to be completely wrong. The green line is the legendary basis. The condition number stays nearly flat across all degrees. The reason is that legendary polynomials are orthogonal. Each polynomial in the legendary family is independent of the others mathematically. They do not interfere with each other inside the design matrix, which keeps the matrix stable and reliable to solve. Now looking at the scale function in the code, before applying legendary polynomial, I scale the time variable from its original range of 0 to 365 down to interval -1 to +1. This is what one line function does, and it is required for legendary orthogonal to hold. Now, so uh, now this slide shows the same result from the code. The monomial condition number grows steeply while the legendary condition number stays stable. The scaling formula that maps any interval to -1 to +1 is shown at the bottom here. Now to conclude what this experiment showed, first the polynomial regression fits a polynomial to data by minimizing the sum of squared errors. And second, the degree controls model complexity. Too low causes underfitting while too high causes overfitting. And third, training error always decreases as degree increases, but that alone does not mean the model is good. And fourth, the legendary polynomial basis keeps the computation stable at higher degrees, which the standard monomial basis does not. So this is my this is my assignment.